A vertical rod BA of length 4L has one end B fixed to a horizontal surface with the other end A vertically above B. The ends of a light inextensible string of length 4L are fixed to A and to a point C, a distance 2L below A on the rod. Okay, so this distance here is 2L. We have one continuous piece of string of length 4L. We're given that a small mass m kilograms is tied to the midpoint of the string. So that means that this distance here is half of 4L, which is 2L, and this here is also 2L. The mass rotates with both parts of the string taut in a horizontal circle with uniform angular velocity omega. So we want to get the tension in each part of the string. So we want the tension in this part and in this part of the string. The first thing to notice here is that we have an equilateral triangle. The three sides are each of length 2L, so the three angles are the same and they're 60 degrees. Let's look at this picture here. Now, tension is a force that acts away from the particle that's attached to the string. So T1 acts away from the particle and T2 acts away from it. Of course, these two tensions are not necessarily the same, so you better call them different names. So T1 and T2 are not the only forces acting on this mass. We have its weight, of course, which is its mass times g. We are given that the mass moves in a horizontal circle, so its acceleration has no vertical component. In other words, the particle is not moving up or down. So that tells us that the sum of the vertical components of the three forces acting on the mass is 0. Let's look at the vertical component of T1. Well, that's just the magnitude of this vector T1 times the cos of 60. We have a pair of z angles here. Now what about downwards vertical components? Well, these two vectors have vertical components that are pointing downwards. So we have T2 cos 60 plus mg. So the sum of the magnitude of the downwards components must equal the sum of the magnitude of the upward components. So we equate T1 cos 60 with T2 cos 60 plus mg, and I've rearranged it like this. What is the cos of 60 degrees? Okay, it's a half. Half appears here, so if I multiply all this equation by 2, I get T1 minus T2 equals 2mg. Now we are given that this particle moves at constant speed in a circle. It's a horizontal circle. And we know that if that's the case, at any instant of the particle's motion, the resultant force on it points towards the center of the circle. So I will call the resultant force vector F. Of course, it's constantly changing, as we know, but at this particular instant, the resultant force vector is pointing towards the center of the circle. Its magnitude is always constant. Well, how do we get the resultant force? Well, we just get the vector sum of T1, T2 and the weight vector. But to get that vector sum, we only have to consider the horizontal components of these three vectors, because the vertical components sum to 0. Now the horizontal component of the weight vector is 0. It's in the vertical direction. So the resultant force F of the three forces must be just the sum of the horizontal components of vectors T1 and T2. So we imagine getting the horizontal component of T1, which is this here, and adding onto it the horizontal component of T2, which is this vector here. Obviously this is not drawn in proportion. The sum of these two green vectors should give us vector F. So if I'm going to make it look consistent with this diagram, I suppose I should extend vector F. So it's out here somewhere. Okay, the horizontal component of vector T1 is just T1 sine 60. I can show the horizontal component up here and multiply the hypotenuse, which is magnitude T1, by the sine of 60. And I do the same for T2. So I sum the magnitudes of the horizontal components because the magnitudes are pointing in the same direction. And the sum of those magnitudes must give us the magnitude of the resultant force. And we know that for a particle moving at uniform circular motion, that is given by the mass times the centripetal acceleration, which is r omega squared. So if we check back here, we see that we are not given the mass, we are not given the radius of the circle, we are not given omega. Now in sword form, the sine of 60 is root 3 over 2. So we can multiply everything by 2 over root 3 to get T1 plus T2 equals 2 over root 3 m r omega squared. Now we are not given the radius, but we want our answer in terms of m, l and omega. We want t in terms of these quantities, not the radius. So we'll have to use some geometry here to get r in terms of l. See, this triangle has sides of length 2l. This particle is at the midpoint, so this distance here is l, which is equal to this here. Two of them make 2l, you know. So we can just use Pythagoras to get r. So r is one of the short sides of this right angle triangle. So r squared, or r is the square root of the longest side squared minus the other short side squared. So it's the square root of 3l squared. So r is root 3 times root l squared, which is l. So now we have two equations in T1 and T2. So if we solve these equations, we will be able to get T1 in terms of m, l and omega, and also T2 in terms of m, l and omega. So we treat the unknowns as just being T1 and T2. So we have two equations and two unknowns. Conveniently, these cancel out. So what's the easiest way to solve between these two equations? Well, you can see that if you just add the left-hand sides together, the T2s will cancel out. So we'll get 2T1 on the left. Now add the right hand sides together. It's 2mg plus 2ml omega squared. Okay, so we can factorize m out of these terms. So now we have T1 in terms of m, l and omega squared. So we can plug this into either equation to get T2. I'll plug it into this one here. So I need to I've rearranged this equation to make T2 the subject. So T2 is T1 minus 2mg. So I plug this thing in for T1. Okay, so we get 1mg minus 2mg. I multiply the m back in here. So that's minus 1mg, and factorized m out. So we get m into l omega squared minus g. As an aside, notice that these actually make some sense. We can see that T1 is greater than T2 because L omega squared plus G is greater than L omega squared minus G. Okay, if you add G onto L omega squared, you'll obviously get something bigger than if you subtract G from it. And that kind of makes sense because T1 has to counteract the weight of this object. So we might expect the tension in this string to be greater than the tension in this string. At a given instant, both parts of the string are cut. Find the time in terms of L which elapses before the mass strikes the horizontal surface. First of all, notice the height of the mass above the horizontal surface. Well, we can see that the height is, well, this distance here is L. So and it's L up here as well, of course. So we have 4L minus L, which is 3L. So the mass will fall a height of 3L. Now if the string is cut, the mass will initially move in the direction of the velocity, which is, well, it's in the horizontal plane. So the velocity vector is tangential to this horizontal circle. So the mass will move in that direction. But then, of course, as soon as the string is cut, gravity is acting, so the mass is obviously going to fall to the ground. But the horizontal velocity of this mass is immaterial. As soon as the string is cut, the only force that acts on this mass is gravity, which is vertically down. And the acceleration due to this force is the acceleration due to gravity g. So it doesn't matter how fast this mass moves in the horizontal plane. As soon as the string is cut, it'll fall at the same rate as any object, even if it's dropped from rest. We could even imagine, say, a gun that fires a bullet from a certain height. So the bullet is fired horizontally, and eventually, of course, it'll fall to the ground. Well, the bullet will take the same time to fall to the ground as it would if the bullet was simply dropped from rest. That's because the only force acting on the bullet in both cases is vertically down. As soon as the bullet is fired from the gun, there is no horizontal force acting on it. Well, if we ignore air resistance. The only force acting on it is vertically down, force due to gravity. So in both scenarios where the bullet is fired or simply dropped from rest to the ground from the same height, it'll take the same time to hit the ground. So we are dealing with a problem involving constant acceleration. This is the acceleration in the vertical direction. There is no acceleration in the horizontal direction because there's no force acting in the horizontal direction. So s is the vertical distance travelled. U is the initial speed. So, well, u would be the initial speed in the vertical direction. But of course, the initial speed of the mass just before the string is cut is 0 in the vertical direction because the mass was always moving in a horizontal plane. So we set u equal to 0. Well, s, the distance travelled in terms of L, is 3L. So 3L is equal to half gt squared. T is the time taken for the object to hit the ground. Rearranging, we get t equals root 6L over g seconds.